Hello everyone, welcome. My name is Abhijit and I'm going to give you a walkthrough today on the project, the Tressa GPT model based on the GPT architecture. Here we have the project open. It's written in Python and using PyTorch. So basically this is the class, the Tressa GPT model. Okay, so this is the Tressa GPT model, and in that you can see we are loading the config here. Config is simple, which is coming from this file. So let's see what is the configuration here. So configuration is this. We have model name, we have embedding dimensions is 384. We have 384 dimensions, and then number of transformer blocks is 6, and you can see number of heads is 6. So basically we have 6 transformer blocks stacked one behind the other, and the number of heads in the multi-head attention block is 6. So we stack 6 attention heads for a single transformer block. Okay, so the vocabulary size is 1 million. This number. The vocab size is 1,277,000. So this is the same tokenizer which is used by GPT-3 and GPT higher models. So that's the thing. And dropout here is 0.1. So dropout is really important because sometimes the perceptrons don't work, some of them, and some of them work more. Okay, so just to make sure that all the perceptrons work properly and they update their weights, we use a dropout. And this is FFN expansion. So basically this expansion happens in the feed forward neural network layer, where for example, let's say 384 dimensions, the input is 384 dimensions, it is expanded into 5 times. Generally it's 4, but in this model we have done 5 times, so that we get a very good understanding of the context which is generated by the transformer block, by the multi-head attention block. Okay, so we are expanding the in the feed forward network, we are expanding by 5, as I just told you. Batch size is 32. So if the GPU is very good, if the GPU has good VRAM, then you can have a batch size which is 32, 64. But generally, 32 is on the higher side, so you can start with 8, 16 like that. So block size is 128. So block size, so for example, since we know that the GPT has to predict the next word, so we are starting from actually 64 as well. I think 128 here. So first 128 tokens. Let's say you have a text. Let's say you have some text like let's say you have some text which is like 200 characters, 200 words. So it's the tokens basically, I'm sorry. So let's say you have a block size of 128. That means the token IDs, 128 token IDs are there, and then we move the window to 1 by 1, right? So the next token the GPT model has to predict. Then this is the learning rate. So the rate at which the model updates its weights. Max steps. So these are the steps for the 5 billion tokens. We'll see this for the iterators. So like that, there are some settings here. Okay, so checkpoints and shuffle buffer size. This is to shuffle the data set, and so forth. Okay, so these are the main things which we covered. We are also using a data set which is FineWebEDU, which has 10 billion tokens, I think, and we are using just 5 billion of them. And dataset size is this is just the name of the dataset, and the checkpoints folder, and the device is MPS. If I run this on a Mac, then it will be MPS. If I run this on a CUDA environment, it will be CUDA. Otherwise, it will be CPU. It is highly recommended that we run this training on MPS or CUDA, and preferably it's CUDA. CPU, it will take 10 times or even 20 times the time to train the model. For example, I finished this training in 2 days. So on the GPU, it will take, just imagine, 2 days into 30 times. So you never want to train your model on the CPU, sorry. So let's go ahead. So this is the config. The embedding dimension, as I told you, it's 384. And the token embedding, this is really important. So in this line, the for the full 1 lakh tokens, we create a vector which has the embeddings for all of those tokens. Okay. And then next we have the positional embedding. So we are using a sinusoidal positional embedding, so that so we are generating a positional encoding for each and every token using the formula of sines and cosines. Basically, by using the property that each and every number generates a unique wave, and we are using a different frequencies to generate different waves, and then from those waves we sample the numbers so they come out uniquely. So that is how the positional embedding works. And then finally the dropout, as I just told you, dropout is used to make sure that all the neurons work equally. Okay. So now here we have the transformer block. All the transformers are stacked. So currently we're using 6 transformer blocks. So 6 transformers blocks are stacked one above one behind the other. And the module list is important. It helps the transformer blocks get registered under the module, under this module, Tressa GPT model. The module list does that role. And then we have layer normalization. So after the output comes from the transformer block, we need to make sure that the outputs are well defined in the limits. The mean is 0 and the variance is 1. That is very important. Otherwise, we'll have the exploding gradients problem and many other problems. Gradients problem basically, and so many problems. So since we are doing lots and lots of multiplications, we don't know how things might go out of control. So layer normalization helps training to be very in control basically. The learning modeling head. So this is the one. It's actually generating the logits. It's used for generating the logits basically. So we are expanding from embedding dimension to the vocabulary size. So basically this head will predict which is the next token. So as you can see, the vocabulary size. So this is nothing but a vector of this shape. Embedding dimension here, embedding dimension and vocabulary size. So just imagine an array which has 384 rows and 277 columns. So here whichever token will be produced next by the model will have the highest probability in the matrix, in the tensor. Let's go to LM weight. So this, we are tying the weights of the token embedding and the LM head because we don't want the embeddings to be different for LM head and the token embeddings. Because if let's say we have a token, token of president, let's say. So we don't want the embedding of president to be different in token embeddings and to be different in the language modeling head. We want the embedding to be same for in both of these tensors, right? Because president is same everywhere, right? The meaning should be same. So that is why we are tying the weights of the token embeddings and the language modeling head, so that the language modeling head doesn't end up in different embeddings, and the token embedding doesn't end up in different embeddings. So for example, I'll give you an example. So let's say, for example, the embedding 0.2, 0.3, 0.5, just for an example, and so on. This embedding, if the language modeling head has a different embedding, then it doesn't make really much sense, right? Because the language model head is also talking about embeddings and the same embeddings and the Token embedding also is talking about same embedding. So point is, both the language modeling head and the token embeddings, the embedding should be same because both are talking about the same token. Simple. Okay, let's ignore this for now because this method was added for LoRa. Okay, low rank optimization, low rank adaptation. Then forward method. This is actually the method which computes the output of the model. So here we are just initializing the various modules, but here we are actually, the modules are at work. So as you can see, the inputs are given, then we generate the token embeddings. Okay, and then it goes through the transformer here. As you can see, we are sending this array of the tokens to the GPU device. Okay, then we are doing dropout. So basically what we are doing here is we are adding the token embedding and the positional embedding. Okay, because ultimately I love cats and cats love I. They are different sentences which mean different things. If there are no positional embeddings, then both of the sentences become the same. So we add the token embeddings to the positional embeddings and we normalize it, but the normalization is happening already inside the transformer block, so we directly send it. Okay, and then once the data comes out from the transformers, the tensors come out from the transformer block, we have a layer normalization, and finally we return the logits. Okay, so this is the way it is working. So now let's look at the training.py. So this is little simple. So we are using a data set, as I just told you, fine web edu, and it is making an iterator. Let me go to that place, data.py. Okay, so let me show this. So streaming dataset, we are not downloading the full dataset first. We are not downloading the full dataset. We are streaming it from Hugging Face because not required. We don't require to download the whole dataset. Hugging Face has datasets library has a feature where you can stream the rows stream the data basically which you want to train your model on. So we have a iter method which is required to be implemented by the iterable dataset, and we are this model, this line here, it automatically pulls the data from the Hugging Face as required, and we are also maintaining a language score. We want high quality sentences or English passages only. We don't want any passages which have HTML or low on language score basically. So then we tokenize it, and we add a end of sequence token, and then we return the tensor. Okay, and here is the place where we are. So first, for the inputs, it will have 0 to 128, and for the output, tensor will have 1 to 129, right? So then 129th token is what GPT has to predict. So the input size, the X will be, as you can see, there is a +1 here. See, I +1. So basically, we are giving first 128 tokens as input, and next window 1 to 129 is expected in the output. Okay, so that is the way tokenization is working. So let's go back to the model. Let me explain how the transform block is done. As you can see here, we have embedding dimensions, and we have a layer normalization as soon as you come inside the transformer block, and then we have a dropout to make sure these layers work properly. As I just told you, sometimes some neurons become lazy, the perceptrons become lazy. Dropout layer also, and we have layer normalization. We'll see this. So we'll see the forward method. So we are getting the forward the context vector from the multi-head attention block. Okay, the context vector, it is the vector which has understanding of the tokens which surround it. Then we are adding it to the inputs. This is the shortcut connection. Then we are normalizing it again, and then we have a feed forward network. Then we have a dropout to make sure that this FFN out, this feed forward network works properly, as in no neurons. We should not have the situation where some of the neurons are working more hard and some of the neurons are working less. Okay, and we return the output. So this is that transformer block. And then let's go to the multi-head attention block. So as the name says, it is just single head attentions stacked, as you can see, torch.cat, single head attention. So basically we have, we are embedding dimension is 384. Let's say we have 6 attention heads. So one attention head will deal with 384 by 6, whatever the number is. I think 48 around. So dimensions per head. So every head will work on 48 dimensions basically. So this is to make sure that every head gets a different perspective of the input tokens. So multi-head attention block is very important because every head will get a different perspective of the input tokens, so that it can compute a good output. Okay, because every sentence can have many meanings, as we see, you know. So multi-head attention helps in that way. So we have the modules list. It helps to register all these single head attentions inside the module, this one. And finally we have outproj. So this is a layer to refine the output of the multi-head attention block. Okay, see, we are getting so many heads. In the previous models this outproj was not there, but recently I think it helps the output improvement by 5%. So this tensor helps to refine the outputs of the multi-head attention block. Okay. Yes. So let's move on to the forward method of, now see, let's move on to single head attention. So in the single head attention, as the head dimensions are here and the embedding dimension is here, so we have a query key value vectors here. This is the heart of the transformer block. So basically, if the product of query and key is higher, that means we have to give more value to that particular token. So this token attends to that token more. That is the understanding. And as usual, we have dropout. So in the forward method, we have the query key and this. And so the first we multiply all the input embeddings with the query key and value vectors. And then we do a transpose of the key and matrix multiplication with the query. And then we have upper triangular matrix, and so that the future tokens don't influence the current tokens. And then we get the attention score. And after that, we have a torch.softmax to make sure that we land into probability zone. Okay, we don't want simply weights, we want probabilities. For example, attend, let's say the cat sat on a mat, right? So the cat should attend to the mat more when the sentence is getting translated. So like the percentage comes out after this, like 20%. So the cat should attend around 20% to the mat keyword or the token. So that score comes out here. And then the attention weights, so softmax turns this into probabilities, and then once we have the probabilities, of course we finally multiply it, attention weights, with the value vector. So this is the heart of the transformer model, and we have sinusoidal position encoding here. I purposefully decided to go with sinusoidal positional embedding. I know there are more advanced methods out there, but as of my learning, I am here. So sinusoidal positional embedding, as I told you, depending on we are using the feature of cosine and sine functions by generating different frequencies, we get different numbers for each and every position. So that feature is getting exploited here. So that's the walkthrough of the model, and let's see how this model is working. So let's load up the model, and just to give you some memory requirements, the memory, I think when I load this model for inference, I think it's taking around 2 to not more than 2 GB in the RAM. Okay, so let me run this uv run python src chat Tressa. So I will see. Okay, so it's loaded now. So why is petrol flammable? Let me ask this. So glass flammable is not the only form of energy that can be used in large quantities. It also has advantages over conventional sources of energy. So as we can see, the answer is not what we want, but definitely the answer, the sentences generation makes a lot of sense. Okay, the sentences which it is generating makes a real lot of sense. See, it is the sentence structure is good, the grammar is right, the subject object relations are good, the adjectives are good. So we can definitely say that we have reached this model is good in the sense of language understanding. Okay, this is definitely the conclusion. So let me ask, who is the president of India? So the president of India is the president of India. So even the last time I got the same same answer. So probably it's making up, it doesn't know the answer. So the point is it's producing a coherent sentence. It is not producing any gibberish sound. It's not jumbling up the tokens, right? It's not producing something which doesn't make any sense. It is making sense. So I would definitely say this model is successful. I think what I will do is I will increase the number of transformer blocks, and I'll also increase the embedding dimension. And I think my next plan is to take it to around 150 million parameters. And this is just the starting. This is my first model in my life, and I'm really happy to get end-to-end understanding of the model. And please stay in touch, and hopefully we make great models. Thank you. Have a good time.